going to talk about parallelograms and basically the converse of every theorem that we had yesterday and the day before. So before we said if something's a parallelogram, then we know following facts about them. The opposite sides are congruent. The opposite sides are parallel. The opposite angles are congruent. Consecutive angles are supplementary. But all of those conclusions required us to know that the shape was a parallelogram first. Today, we're going to work all of that backwards. How can I prove that something is a parallelogram? And basically, it's the converse of everything we just learned. For example, in this first theorem here, it says if the opposite sides are congruent, both pairs of opposite sides are congruent, then it must be a parallelogram. Or if both pairs of opposite angles are congruent, then it must be a parallelogram. So essentially, we're using the converse of everything to make our conclusion about parallelograms. This is one of the examples that you see often, the old amusement park ride. And basically it's saying, how do you know that this is a parallelogram? How do you know this shape is always a parallelogram where this thing's swinging back and forth? And quite honestly, it's easy to tell because if we look at the both pairs of opposite sides, these are fixed lengths. I mean, the distance between the two pulleys here is exactly 38 feet. The top bar is exactly 38 feet. These bars on the sides are both exactly 16 feet. And since both pairs of opposite sides are congruent, it must be a parallelogram. So why is it always parallel to the ground? Because this segment DC, right through there, in fact, I'll make it red. We know DC is parallel to the ground. It's designed to be parallel to the ground. And since this shape is a parallelogram, AB is also always parallel to the ground. Because opposite sides of a parallelogram are parallel, that's the definition of parallelogram. So it's just a little example of how we use that. If we have a quadrilateral x, w, x, y, z, w is 42, and x is 138, and y is 42, find the measure of angle z, and is it a parallelogram? So again, type problem like this, what are we going to do? We're going to draw a picture. And we're going to make it look kind of like a parallelogram. I'm just not sure if it's exactly a parallelogram. But we'll go ahead and label it w, x, y, z. We're told w is 42 degrees, x is 138 degrees, y is 42 degrees. First question is, what's the measure of angle z? Well, that's pretty easy. We know since there are four angles, it's the number of sides minus 2 times 180 for a quadrilateral, or 2 times 180, so the sum is 360. Then we just go ahead and start subtracting off the angles we have. Well, 42 and 138, that adds up to 180. So subtract the 180, I'm left with 180 remaining, and subtract another 42, and I'm left with 138 for my last angle. Oh, guess what? Both pairs of opposite angles are congruent, aren't they? Therefore, this must be a parallelogram. Okay? Must be a parallelogram because both pairs of opposite angles are congruent. Here's a pretty simple setup. It's going to ask you to find the values of x and y. Now, it's a little bit tricky here. I'm going to give you a little bit of a hint. We're going to solve for x first. And in order to solve for x first, we're going to have to use the opposite sides. And what property has to be true for the opposite sides? Once I solve for x, I'm going to have to substitute that value for x in over here and use that to help me solve for y. So why don't you go ahead and do that? That'll be our first question of the day for our head puzzles. Now that that's done, let's just go ahead and review exactly again how that was done. It was x plus 9 equals 2x minus 1. So x equals 10. And then 10 plus 7 is going to be 17 for y. So pretty straightforward stuff to get that done. Other theorems, other ways of proving that that a shape is a parallelogram. We got a couple, one new one and one that kind of builds on the old. We already knew that if it's a parallelogram, the diagonals bisect each other. We can now use the converse of that. So diagonals converse, that's this one right here. If the diagonals bisect each other, in other words, if this point right here is the midpoint for both diagonals, then that must be a parallelogram. The new one is this one. If I have one pair of sides, okay, one pair of opposite sides are both parallel and congruent. So congruent and parallel. Then it must be a parallelogram. One pair of sides congruent and parallel, it must be a parallelogram. So it's not one pair of sides congruent and the other pair of sides parallel. That obviously wouldn't work. And the reason that wouldn't work, just out of curiosity, could I have one pair of sides parallel and another pair of sides congruent and it not be a parallelogram? Absolutely. Congruent sides, parallel sides, not a parallelogram. Okay? It's got to be the same pair of sides that's both congruent and parallel. If that's the case, it must be a parallelogram. So that's a new one for us. That's not really related to our old ones. Another picture of a doorway in England where the opposite sides are both parallel and congruent. How do you know that SV is congruent to TU? Because it's a parallelogram. Opposites. The fact that the opposite sides here are both congruent and parallel tells me that that shape STUV must be a parallelogram. And if it must be a parallelogram, then all pairs of opposite sides must be congruent. So those two sides must also be congruent. Pretty straightforward stuff. One more question for you today. For what value of X is CDEF a parallelogram? Again, this is one that I want you to work on. It's not terribly difficult, but you have to know your theorems again. What has to be true about the diagonals of a quadrilateral in order for it to be a parallelogram? The diagonals must do what? Or in other words, this point must be what for both diagonals? That should help you set it up. We already know that these two are congruent because of the markings. What must be the value of X in order for this to be a parallelogram? That is your final question and the end of our podcast for today. We'll see you in class.